So when we talk about mineral resources, we can divide those into roughly two main categories, metallic and non-metallic. They're all non-renewable. They're formed as part of that rock cycle in Earth's history over a very, very, very long period of time. It's going to be a lot of vocab that maybe you've heard before, maybe you haven't. Or is any rock that contains concentrations of these valuable minerals. If you hear something referred to as high-grade ore, that means it has lots of the material. If it's low grade, it has less of the material. Oftentimes you'll hear discussion of reserves, like oil reserves. We've talked about that before. But so reserves for any mineral resources will be locations where we can extract those minerals with current technology and at current costs. And reserves can change with new technologies. We discover more sources, and as things that maybe weren't accessible at one point are accessible now. Notice figure 1411 down here at the bottom of page 355. I'm showing the whole life cycle of, in this case, a metal resource. And then this natural capital degradation right up here on page 356 highlights some of the environmental effects of each stage of that life cycle, from the actual mining, extraction, the processing of it, and then the use of those materials. So big focus here on environmental effects of obtaining and using these mining sources. Great point here in this thinking about box on page 356. Okay. Why is it that it's will lower grade ores, right, with less material? Why do they require more energy, more materials, more land disruption, more mining waste, more pollution? Okay. If you think about the second law of thermodynamics, right, what's going on there? Okay. And keep that in mind as we think about mining in the future and how we're finding these things. All right, so we can divide mining into two major categories, surface mining and subsurface mining. Subsurface mining, below the surface, is what you probably think of more often. Seven Dwarfs and hi-ho, and coal mines, things like that. But the book focuses more on surface mining for shallow mineral deposits because it has much more of an environmental impact. Generally what happens with all surface mine is that first all of the vegetation, trees, plants, etc. are removed, and then the overburden is removed. So overburden is all the soil and rock that's on top of the desired mineral. And then that all becomes piles of spoils. Okay, so things we don't want become spoils, and those can then sometimes be used to fill in the land. And then they extract the mineral, they extract it from the ore, and then what's left behind from that is known as tailings. And that extra material can then again be left on the land. So surface mining, and there are nice pictures of all of these. We have open pit mining, which you can see in figure 1413. Strip mining, which we can see in figure 1414. Contour strip mining, and mountaintop removal. So contour strip mining we can see in 1416, and mountaintop removal in 1417. So some of the environmental effects of surface mining, big one is land disruption. Not only are you removing all of the vegetation, so you have a loss of biodiversity and habitat destruction, but you're also changing the contour and the composition of the land. You're removing topsoil, so it's going to take a very long time for that ecosystem to recover. When there's no topsoil, you have less vegetation, you get erosion. That can lead to more flooding. It can lead to water pollution or stream disruption. Sometimes, and then if we look at what's happening with water, there's a lot of wastewater and toxic sludge that's a product of the mining and extraction process. And that's oftentimes stored in containment ponds. And there are horror stories of those containment ponds leaking or bursting and releasing a lot of this toxic sludge. You can pollute groundwater potentially. And the tailings and spoils sometimes end up filling stream beds, and that can change the flow of streams. And so there are a lot of potential problems with mining. I like the connections box on 359, looking at the use of mercury in gold mining. So would not be allowed in the United States, but in some places it is, because not all countries have the same law. So that's the second leading source of mercury from humans after coal burning, which is still the primary source. Under the Surface Mining Control and Reclamation Act of 1977, which is not discussed in your book, mining companies are responsible for reclamation, and that's the cleanup and restoring of surface mining sites. It's very expensive, but very important, because think about all that land disruption we were just talking about. However, it's not always done, and we'll get into that in the next section. Okay, with subsurface mining, as I mentioned before, there's a lot less environmental damage. One potential problem is you could have subsidence, which is when basically the land can kind of collapse if you've dug big holes under it. But there are a lot of increased risks for human health and human lives, like cave-ins and explosions, black lung from breathing in like coal dust, etc. So subsurface mining can be more dangerous, but less environmental damage. A few more things. So 3/4 of solid waste, which is our next chapter, in the U.S. is from mining. 3/4. Okay? We also can have acid mine drainage, which basically is when rainwater goes through the mine itself or through containment ponds and mixes with sulfuric acid, which is naturally produced by the bacteria. And then you get a whole bunch of sulfuric acid that ends up in streams. So not good. Water pollution, you get toxic air pollution. So there's a lot of kind of horrible stuff that can happen from mining. And then even just, so that's all from the mining, and then there's the actual extraction part of the life cycle, where you take the ore, you have the ore mineral, and then you have what's called the gangue, which is the waste, and then that gets kind of piled into the tailings. Okay? The ore mineral itself, oftentimes, there's a process known as smelting, okay, which is using incredibly high heat to release the metals from ores. Smelting produces sulfur dioxide, particulate matter, greenhouse gases, can lead to water pollution, hazardous waste, so all in all kind of horrible. All right, so these are non-renewable resources. How long are they actually going to last? Where are they found? What's going on? So the 5 top countries for non-renewable resources, most of them are really large, coincidentally: the United States, Canada, Russia, South Africa, and Australia. They're not distributed equally around the globe, which makes sense if you think about how they've been formed. There are something known as strategic metal resources, which are super important for the economy and for the military, like manganese, cobalt, chromium, platinum. We don't really have large reserves of those in the United States. And depending on where those minerals are found, it can lead to some interesting political dynamics too, and economic dynamics. If you ever hear of something being economically depleted, what that means is that it's reached a point where it's going to cost too much to find, extract, transport, and process the remaining deposits. So there may still be some there, but it's just not feasible anymore. There are solutions to depletion, and these depletion curves, which you can see right up there on page 361. So recycling and reusing minerals, wasting less, using less, can find a substitute, or maybe do without. All of those things will actually slow down depletion time. So basically, if you look at curves A, B, and C, the total area under all of them would be the same, but how quickly you're extracting it will affect how quickly it's depleted. There's a lot with economics when it comes to mining. Like, you think like supply and demand. As supply goes down, but demand goes up, what's that going to do to prices, etc. But that can be affected by especially subsidies, which is a hidden cost of a lot of these mineral resources because taxpayers are paying the subsidies. Taxes, high taxes or very low taxes on different products, and then tariffs as well. Okay, there's a nice case study here about the U.S. General Mining Law of 1872. Basically what happened is it was a way to encourage westward expansion and gold mining, so you could get public land, so U.S. public land, really cheaply, and then what people could do is then sell or lease that to mining companies, make a lot of money. But what often happened, and can still happen, is that companies declare bankruptcy, and then they're not really responsible for the cleanup because, oh, they don't have any money anymore, which may or may not be true. And the cleanup of abandoned and toxic mines is very often now covered under CERCLA or Superfund, which we'll get to in chapter 21. So again, taxpayers end up paying for a lot of the cleanup. So the book poses like, all right, what about this lower grade ore? that we can find. Is this an answer? So one thing that's like, yeah, let's do that, is we have better technology and better equipment. So we can get these lower grade ores can actually be economically feasible. But the problem with maybe why do we not want to rely on lower grade ore necessarily is there is an increase in cost of the mining and processing. Mining oftentimes, especially the lower grade the ore is, the more water it's going to require. So we have fresh water shortages, and then the environmental impacts are going to increase as well. So one thing you may have heard of before, probably not, but maybe you will at some point, is in situ mining, which so it's like in place. So mining, extracting the material from the ore where it is using bacteria, sometimes genetically modified bacteria or genetically engineered bacteria. So you can extract the minerals without disrupting the land or air pollution, but it's really, really, really slow right now. So kind of using biology, using nature to do that. And then minerals in the ocean, you could get them from seawater, continental shelf, the hydrothermal vents, these things called manganese nodules, but it's really high cost, and there's the issue with who owns the ocean. All right, so what can we do to make those depletion curves last longer and use these materials more sustainably? So we've got the idea of substitution with like the materials revolution, like fiber optics, replacing metal, nanotechnology, which is discussed in this science focus. So who knows what the future will look like with these sources. But we have on page 366 a great summary of sustainable use of non-renewable minerals, recycling being huge, reduce, reuse, recycle, and then a great case study looking at how one company helped to reduce their waste in manufacturing and how that's made an impact. So that is chapter 14 in a nutshell.